Welcome to this video on list coloring and Thomason's theorem. In order to get the most out of this video, you should have the prerequisite knowledge that is being shown now in the screen. There are links to videos on these topics in the description. If you are watching this video, you probably already know about the four-color problem posed by Francis Gaudry in 1852 when he noticed that 4 colors suffice to color a map with the counties of England. You probably also know how these problems can be translated into graph theoretical terms and how it was proven many years later with a very long and complex proof with many cases that have to be checked by a computer. This problem opened up the area of graph coloring, consisting of assigning labels or colors to elements of a graph in a way such that certain constraints are satisfied. The most common and well-known form of graph coloring is vertex coloring, where the vertices are assigned colors and no two adjacent vertices can have the same color. But there are also other types of colorings. For example, edge coloring, where it is edges that are assigned colors and no two incident edges are allowed to have the same color, or total coloring, where both edges and vertices are colored, or acyclic coloring, and so on. The one specific variant of graph coloring I will be discussing in this video is list coloring. And why did I decide on this one? That's because there is one result in this area which has a especially nice and short proof that I want to show you. List coloring is just like regular vertex coloring, just that each of the vertices has a particular list of colors you have to choose from. So you don't select the colors of the vertices from a fixed set of colors common to all vertices, but instead, for each vertex, its chosen color must belong to its own list. Unlike in the usual vertex coloring, any two adjacent vertices must have different colors. We call an assignment of lists to each of the vertices of the graph a list assignment, which we usually denote with the letter L. And we say that a graph is L colorable if it can be colored with colors chosen from the list of L. We say that the list assignment L is a k-list assignment if each list has at least k colors, that is, if all the lists have length at least k. Recall that the chromatic number, usually denoted by the Greek letter chi, is the minimum number of colors needed to color the graph in our old regular vertex coloring. Now, we say that the list chromatic number, chi sub L, of a graph G is the minimum number k, such that for every k-list assignment L, G is L colorable. Or, in other words, it is the minimum length of the lists, so that if each vertex has a list of that length, then there must exist a proper list coloring, no matter which particular list assignment is chosen. We can see that the list chromatic number has to be at least the usual chromatic number, since assigning the same colors to each list is a possibility. However, the list chromatic number can be higher than the regular chromatic number for some graphs, and at least for me, it was not immediately obvious how this can be possible. I mean, if not all lists are equal, then it means that you are adding extra colors, so it should be easier to find a coloring. Shouldn't it? Let's see an example to find out why this isn't true. And we can use as an example the graph we have right here on the screen. This graph is bipartite, so it can be colored with 2 colors. With this list assignment, with 2 colors per vertex, it is impossible to find a coloring. If we choose, let's say red, in this vertex over here, then we must choose green on the vertex right below it. And therefore, in these 2 vertices to the left that are adjacent to these vertices that we have already colored, we have to choose blue in both of them, but they are adjacent vertices, so this is not possible. Similarly, if we pick green instead of red, then we have to pick red in the vertex below it, and Then in the two vertices to the right, we are only left with the option of choosing blue, which again cannot be done. So for this particular two list assignment L, the graph G is not L colorable. Therefore, the chromatic number of G is at least 3. List coloring, or choosability as it is sometimes called, was introduced by Erdos, Rubin and Taylor in 1979. The aspect of list coloring that brings us here is a very natural question. Does there exist an analog of the four-color theorem for list coloring? Erdos, Rubin and Taylor asked themselves this very same question, and conjectured two things. The first one, there exists a planar graph with list chromatic number at least 5. That is, the four-color theorem does not hold for list coloring. But the second thing is that every planar graph has list chromatic number at most 5. So in fact, there is a 5-color theorem instead. So these things were conjectured by Erdos, Rubin and Taylor, but they weren't proven until later. The first conjecture was proven in 1993 by Margaret Boyd, showing an example of a graph with list chromatic number 5, and 1 year later, Carsten Thomassen proven the second conjecture. Now, in every explanation I've seen of this, they skip directly to the proof of the second conjecture, which is Thomassen's theorem. And well, that's what this video is about also, because the proof of Thomassen's theorem is really the nicest thing about all of this. And it's very short and very pretty. But I think it is important to see the example of the non-four-colorable graph, because, well, this is what proves that 5 is really the right number for list coloring planar graphs. And a part of the beauty of Thomassen's theorem is that it does really give the right bound, in contrast to the 5-color theorems for regular coloring, which have also simpler proofs. And besides, proving this is just showing an example of a planar graph with a 4-list assignment L, such that the graph is not L colorable. So how can this be? Oh, wow, this is a bit complex, as you can see. It has 238 vertices. This was the original example shown by Margaret Boyd. And by the way, one of the things Boyd is notable for is proving and disproving conjectures in graph theory with absolutely crazy counterexamples. I mean, look at this. And, well, as I was saying, this was the original example given of a non-4-list colorable graph. And while it is really not that hard to understand once you break it into smaller pieces, instead of explaining this, I'm going to explain a simple example found a few years later by none other than Maryam Mirzakhani. It was one of her first papers. So this one has just 63 vertices, and you can see more clearly how it is composed of smaller pieces. Let's see how those work. Note that each of the vertices has assigned 4 out of 5 colors: red, green, blue, yellow, magenta. The main claim is that in any coloring of this piece of the graph, the color red must appear at some of the exterior vertices. Assume not. Then each of the exterior vertices has only 3 colors to choose. Let's label the 4 vertices in the central square U, V, W, and X. Let's assume we choose magenta for vertex U. Then we can see we are forced to choose blue in vertex V. Otherwise, if we choose yellow for V, then no matter which colors we choose in the other 2 vertices, the 4 vertices of the top square will have 4 different colors, and therefore it will not be possible to color the central vertex of the square. So, assuming we chose magenta for U, we have that V must be blue. In a similar way, since vertex V is blue, vertex W must be green, since we have a similar situation with the colors here. And again, once we have colored vertex W green, vertex X must be yellow. And now note, in this last square, we again have that X being yellow implies that U must be magenta, which is okay since we already chose you to be that color. But now, the central vertex cannot be colored, since the 4 vertex of the central square have 4 different colors. Therefore, we conclude that our initial choice of coloring U magenta was not correct. Let's color U green. Now we're going to be rotating the cross clockwise, but the situation is the same as before, and by analogous arguments, we have that U being green implies that X is blue, X being blue implies that W is magenta, W being magenta implies that B is yellow, and B being yellow implies that U is green. So again, we find that the 4 vertices of the central square are colored in different colors. Now, note that we have seen 2 chains of implications, and that coloring any of the 4 vertices, not just U, with any of the colors in these chains forces the color of the other vertices in a way such that all the colors in the central square are different. So there is only one choice left for each of the 4 vertices, and it results in 4 different colors again. We conclude that it's impossible to color the graph without having the color red appear in the outside. Now, we can make another copy of the graph, but with the colors permuted, so now it is green the color that is forced to appear in the outer vertices. Additionally, we can fuse the graphs since 2 vertices have the same list assignment. We make another 2 copies, so that in these 2 copies, the colors that must appear in the boundary are blue and yellow. Now, we add a node with the list of red, green, blue, and yellow that is connected to all the vertices in the boundary, and voila! We have our example of non-4-colorable graph, since we deduce that all those colors must appear in the neighbors of this vertex. Okay, so now that we have seen that lists of length 5 are needed, we are going to see that lists of length 5 are enough. This is the celebrated theorem by Carsten Thomassen. How did he prove this theorem? Well, the first thing to notice is the following. It is enough to prove the theorem for triangulations. Triangulations are connected planar graphs in which every face of the graph is a triangle. Note that every planar graph can be turned into a triangulation by adding some edges, and if it is 5-list colorable after adding those edges, then when removing them, the colorings will still be valid. In fact, in this proof we will only assume that the graph is a near triangulation, that is, a planar graph with an embedding in which every face is a triangle, except possibly the outer face. We will require that the outer face forms a cycle at least. If it is not the case, we can add some edges to fix it. Okay, now we want to prove that every near triangulation is 5-list colorable. Now what? The key idea in Thomassen's proof is proving something stronger. We will not only prove that for every list assignment with lists of length 5, the graph can be colored according to assignment. We will also allow list assignments in which some lists are shorter. Here is the full statement. Let G be a near triangulation with outer face C, and let X and Y be 2 adjacent vertices of the other face. Let L be a list assignment on G such that first, we require that the lists have length at least 5 for all interior vertices, that is, vertices that are not on the outer face. For vertices in the outer face, we only require lists of length 3, except for the 2 vertices X and Y, for which we don't even require that. We only require that they have one color, and obviously it can be the same color for both vertices, since they are adjacent. So the thing is that we allow list assignments with shorter lists on the vertices of the other face. But why? Shouldn't this be harder to prove? The answer is no. This stronger fact is easier to prove. Why? Because we are going to use induction to prove this, and therefore we benefit from a stronger induction hypothesis. So without further ado, let's prove this theorem. We will use a strong induction on the number of vertices of the graph. The base case is when we have a triangle with 2 vertices assigned one color and the third one with a list of 3 colors. It is clear that in each case the graph can be colored. Now, let's do the induction step. Assuming that the theorem is true for all graphs with less than n vertices, let's prove it for a graph G with n vertices. We will do 2 cases. The first one is when G has a chord, that is, an edge between 2 vertices of the other face which is not in the other face itself. Here, we can split the graph into 2 parts by the chord, duplicating the vertices of the inputs of the chord. Now, by induction, the part which contains the vertices x, y can be colored. Let's modify the list assignment of the other part so that the 2 vertices of the chords are assigned lists of length 1 with the colors that were selected in the coloring of the first part. Then, by induction again, the second part admits a coloring. Since the colors of the duplicated vertices coincide, we can fuse the 2 parts to get a coloring of the 4 original graphs, as desired. Now on to the second case, when G has no chords. Let U be the neighbor of Y in the outer face other than X, and let V be the neighbor of U in the outer face other than Y. Recall that we assumed that G was a near triangulation. That implies that there is a path from Y to V through the neighbors of U. Now, do the following. Choose 2 of the at least 3 colors assigned to U. The color assigned to Y must not be one of the colors chosen. So if U has 3 colors assigned, and one of them is Y's colors, the other 2 must be chosen. Now, let's remove vertex U. Let's also erase the 2 colors we chose from the list of the interior neighbors of U, but not from Y or V. And now, every vertex in the outer face other than X and Y has at least 3 colors, so by induction this graph with U removed can be colored. And now we can add back U, noting that none of its neighbors except for V has any of the 2 colors we removed. V might have one of them, but Y will not, since we specifically chose the colors not to include Y selected as color. Therefore, we can extend the coloring to U with one of these 2 colors, whichever is not in use by V, and G can be colored as desired.